Oh, I see these numbers going up. Hi, everybody. We are just going to give it about 60 seconds because that attendee number is going up, up, up. So we'll give everybody about a minute to join, and then we will get started with Jay Bell from Trellis. And Jay, I'm going to need you to come on stage.
I'm here.
Great.
I thought you were bringing me on stage.
I don't know that I have the ability to. I think Gabriella does, or if I do, I don't know that yet.
Before you told us that you were the expert, so.
Yeah, well, she's very kind. We are doing our best here. All right. It looks like we are at almost 30 people, which is great. Hopefully some more will join us. But thank you to everyone that is joining us for today's session, AI deduplication using vector stores and LLMs to improve constituent matching. I am Lizzie Schaefer, the GM of Blackbaud Social Good Startup Program. Joining me today, it is my pleasure to introduce Jay Bell, the CTO and co-founder of Trellis, Blackbaud ISV partner and former participant in the Social Good Startup Program. Friendly reminder before we get started to please take the session survey that we will be launching at the end of this and all other BB Dev Days sessions. The top 3 rated sessions from BB Dev Days will get a golden ticket to BBCon in Seattle in September. So it's really important that you give us your feedback on the sessions that you love so that we can make sure and get those people out to the West Coast in September. Vote for Jay. So with that, I will be hanging out in the chat. If anyone has questions or requests for more information, just put them there and we will get to them at the end. Or I will make sure that Jay has everything that he needs to follow up with anybody that wants to chat after. So with that, Jay Bell, take it away.
Amazing. Thank you, Lizzie. I appreciate it. Okay, so the chat's over here. So if you guys see me looking over to the right a little bit, I'm looking at things that you guys are sending me. So like as Lizzie was saying, today we're going to be talking about AI duplication using vector stores and LLMs to improve constituent matching. If you don't know what most of those words mean, don't worry, we're going to go through it all, kind of break it down, what these hot terms actually mean when we're talking about them in practice versus what, let's say, pop culture has taught us to think that they mean. So I'm Jay Bell. I'm the CTO and co-founder of Trellis. We are founder of Trellis. I'm an Angular Google developer expert, an NX champion, and I co-host a couple podcasts, the Angular Plus Show and the This Is Learning podcast. And I'm a big open source advocate. I work on open source a lot of the times. I try to open source things at Trellis. So I've gotten involved in quite a few different open source projects, and I've been trying to get into the open source LLM kind of space as well. So that's kind of where this all bubbled up from. So who are we? We're Trellis. We're a fundraising platform for charities, an all-in-one tool, everything charities need. Why am I talking about Trellis when I'm here to talk about AI? Well, our customers process a lot more on Trellis, which means there's a lot more donor data to go through. And we all know, I would assume that most of us know that working with charities that have these CRM systems where there's a lot of data going in, dealing with all these duplicates and extra information can be a little bit difficult. Computers aren't quite as good at pattern matching as we are. So when charities like GBGH, Georgian Bay General Hospital here up in Canada, process so much more money with Trellis, they have so much more donor data going into their CRM. And that means that we have to be more diligent about what data we're deduplicating, what constituents we're matching with their existing constituents. So at Trellis, we've built this complex system for constituent matching by doing our best to normalize data. But that's complex. It's not perfect. There's edge cases. We all know how donors enter their data, how users enter data just in general, right? It's never consistent. So our charities have this problem, right? And it's not just a problem with our platform. It's just a problem in general where they have this influx of donor data when they have a successful event. And they need to make sure that that donor data is actionable. They need to be able to look up donors and know who donated what and what Jay Bell that was from the event. If there's 3 Jay Bells in Razor's Edge, they don't really know what Jay Bell to action, right? When all 3 of those Jay Bells could have been the same Jay Bell. So that's kind of where this concept came from, was trying to figure out how we can build a less complex system from our point of view as the developers for Trellis. Obviously, AI is very complex, but luckily there's a lot of companies out there making this a lot easier for us. So to try and solve this problem, I started investigating using AI to do this deduplication process. So we're going to talk about using vector stores and LLMs to improve constituent matching. So you're probably thinking, like, what exactly is AI in this context, right? Like, just use AI, right? Like, that's kind of a big thing in the world right now, but we need to get a little bit more specific, right? We can't just like use AI in Razor's Edge, right? What's a vector store? You're probably thinking, if you're not a developer, you're probably wondering what a vector store is. You might even wonder what a vector is. We're going to go over that. Does LLM stand for Linguini Loving Marmoset? Spoiler alert, it doesn't. So we're going to go through that. Is AI going to take my job? Now, for some of you, the answer is hopefully. Some of you, maybe not hopefully. But if your job is data entry, if your job is manually going through your constituents in Razor's Edge and trying to compare them, like using maybe the duplicate search within Razor's Edge, right? You still got to do that manually. It's still a lot of work. It's still boring, right? You as a human, we are all flawed. We're not perfect at this, even though we are better than computers at doing pattern matching just by looking at the data. So maybe we want AI to take our jobs in this exact situation. And then the last question is, how can my application solve the two constituent problem? So look out for some Easter eggs. This is just a little fun aside. Look out for some Easter eggs throughout this presentation. There may or may not be a test at the end. I don't know. I hope you like them. I hope you see them. So what exactly is AI in this context? Well, you're probably thinking like Terminator. You might even be thinking this horrible robot that's attempting to save a ball from going in the net, right? This isn't really what we're talking about here, right? As of today, AI is more akin to fancy autocomplete. When the media and companies and other people talk about AI, we've been trained by pop culture to think of what's called AGI, artificial general intelligence. Skynet, that would be more of what we think of as AI. Currently, what we have in terms of AI is called an LLM, a large language model. And it's really just thinking, the LLM has been trained on this massive set of data from the human world, right? The internet is obviously a massive source, scraping websites and blogs and all this kind of stuff. So what LLMs do is they attempt to guess the next token or word or letter that will come based on what was previously generated. So it's more of like a statistical generation than it is actually intelligent, right? It's not necessarily thinking the way that we do, right? It's not conscious, let's say, right? Whereas like Skynet became conscious, and that's kind of the differentiator there, right? So on the left here, this is kind of like just a very basic explanation of what an LLM does. If I type, or if an LLM starts generating hello, what's more likely to be the next word? World or there, right? And then it does this repeatedly over and over and over again and gets more and more consistent's not the right word, but the more it generates, the more context it has to continue generating to answer the question. Now, of course, this is a massive oversimplification of it, but I wanted to kind of break down the difference between an LLM versus an AI or AGI, as we would generally think about it, because we've been trained by Terminator to think that an AI is going to take over the world. Not saying it's not going to one day. Okay, so vector stores. You're probably thinking, we were talking about AI. Well, nowadays, currently, a lot of the companies out there that are building AI applications are using a concept called retrieval augmented generation and or in combination with prompt engineering. So what a vector store allows us to do is it's a storage mechanism. You could swap it out for some other storage mechanism. It could be a document store like, Google Docs or whatever, right? We're storing text files and text information, but we're retrieving information from the store, which is the retrieval part. And then we prompt the model, the LLM or the AI, I'll use them interchangeably throughout this presentation, and then we feed all of that information into the LLM with our question. So maybe we want to know what's the most common first letter of a US president, right? Maybe we scrape the Wikipedia page for all US presidents and then feed that in. We augment the generation to the LLM, and then the LLM has the context that's needed, right? So a vector store allows us to search and query for data. We'll get into exactly how that works next. So you're thinking like, what's a vector, right? You were just talking about documents and text data, Jay, right? Well, at its most core level, a vector is an arrow. It's a directional thing. Two vectors can be similar. They can be complete opposites. Maybe they're pointing in completely opposite directions, right? But at its most basic level, it's a directional arrow of some sort, right? So theoretically, a vector can have any number of dimensions. In practice, vectors that have a very high dimensionality are kind of inconceivable to the human mind, right? We perceive our world in 3 dimensions, with height and depth, but we're not vectorizing data in 3 dimensions when it comes to these vector stores and retrieval RAG applications, right? They can have hundreds or even thousands of dimensions. You're thinking thousands of dimensions. What does that even mean? Well, like I said, it's inconceivable to the human mind to think of something that is 512 dimensions, right? So TensorFlow, which is a Google project, vectorizes in or embeds. So the concept is called embedding. So you embed some text to generate a vector from it. So it has 512 dimensions. OpenAI embeddings are 1,536 dimensions. And Mistral, which I believe is a French startup, their embeddings are 1,024. There's pros and cons. Obviously, the higher dimensionality you have, the more complex the system is, et cetera, et cetera. So how do vectors help us find similar data? Well, let's imagine we have these 2 vectors here. We have JBell all lowercase, and we have JBell with a capital J and a capital B. These vectors are similar. They're not the exact same, though, because from a computer's point of view, a capital J is different than a lowercase j, and a capital B is different than a lowercase b. So let's add another vector in here, and this is where Lizzie makes a surprise appearance. Lizzie obviously is very far away from JBell in terms of the actual value that we would assign to it, assign to the text, right? So if I were to store these 3 vectors in a vector store and query for, maybe J with a lowercase j, Bell with a capital B, and say, give me the top 2 based on similarity, I would be given the 2 green lines back, the 2 green vectors back, because Lizzie is just that text is just so much different than JBell, right? Whereas if I was to query for something like Lizzie all lowercase, I would get the Lizzie vector back because that vector would be closer to the vector that Lizzie's name gets embedded to. So how is this helpful for constituent data, right? Like let's link this back to actually something actionable and usable. We all know how bad users, and I'm not just talking about donors, just users in general, we're all the exact same when it comes to this, bad at entering data. We misspell things, we capitalize things differently, we'll use an abbreviation one time, but not another time, right? There's all these different representations of data where technically they mean the same thing and functionally they are the same thing, but they're written differently, right? We as humans are able to know that 7th is the same as 7th, right? But a computer can't necessarily know that without some additional normalization. That's kind of what Charles currently does, is we built a system that will normalize data as best as possible to do some matching, and then use Levenstein distance to figure out some kind of like flexible amount that it's okay to be off by. But that's complicated to contain, to build a system like that. That works 100% of the time. So as you can see, Dwight is saying that these are close, but the computer doesn't really know that, right? But once we vectorize the data or embed the data, now the vectors would be pretty close to one another. Now, pretty close, I'm using that term pretty generically, but it would all come down to the similarity metric you're using, how many dimensions your data is, et cetera, et cetera. But those two vectors would be closer to one another than, say, my home address, because I don't live anywhere near 7th and Broadway in Los Angeles, California. They're thinking like, where's the AI? I thought we were here to talk about AI, right? AI, so the LLMs, is smartest when steered. And when I say steered, I mean using a practice called prompt engineering. So prompt engineering is where you kind of help and guide the model along. And OpenAI provides an awesome best practices here. I'm going to provide a link to this presentation afterwards. So you can get all of these links as well. So really simple. OpenAI, which is one of the big AI companies right now, provides 6 steps. Include details in the query to get more relevant answers. Tell the model to adopt a persona to act like a certain role. You're an expert in data analysis, right? Or you are a data analyst expert. You are an accountant, right? And that helps the model adopt this persona to understand how it should approach the question that you're about to ask. Delineate the information in the query. Use XML, JSON, Markdown, some other delineation method to help the model break down the different relevant pieces of information you're giving it, so it knows like this is relevant to that part of it, and it's relevant to that kind of thing. Specify the steps to complete the task required. In the constituent matching case, it would be something like, first compare the addresses to see if they're the same, and then if there are duplicates, use the last name as a tiebreaker. Right now, obviously, this condition would depend on how the charity or the user's using their CRM and like what they consider to be the same. But this is just an example where you say, do this thing and then do this and then do that and then give me the answer. Providing examples is a great way, because then it knows, it has some cases to look at to know like, oh, this input means this output, and I'll use that same logic to apply to what the user's asking me to do. And then provide specifics on the length and the format of the output. So we're going to be using structured output in some of these examples that I'm going to give you with some actual code. And we're going to walk through matching some constituent data. What does prompt engineering look like in practice? So I'm going to be using a library called LangChain. It just makes it really easy for us to build AI LLM applications by chaining pieces of logic together. So first off, we have our adopting a persona and providing details. So you're an expert in data analysis and matching user entered information in our CRM to reduce duplicates. You should match the input data to the potential duplicates using the following algorithm. And then that algorithm would be provided by the user being the person that's at the charity that's responsible for cleaning up their CRM, managing their CRM, their database manager, whatever you want to call that role. Next up, we have our delineation. So we're delineating the different sections, and we're saying, here's the matching algorithm. Here's your input data, and then here's your possible duplicates, right? So the model knows what the different pieces are to be able to break down and understand the question and provide a valid answer. You can see here that we have an array of prompt messages. So in these LLM applications, usually there's a way to provide like system prompts, and these are more internal instructions. And then human messages, which would be the actual user instruction, right? So if you go to like the ChatGPT website and you just start typing in the box, that would be a human message. Whereas if you were to define some overarching rules that it should follow, I believe it's in the settings, then that would be more of a system message. And it's kind of in instructions like act like this, speak like that, you are this, stuff like that. Specify steps required. So this is where the matching algorithm comes into place, right? So a charity might know in their head how they want to match and be able to explain that in natural language. And that's kind of what we're looking for here. And then output in a specific format. So like I was saying, we can use structured output. So we're going to be using internally, what this is using OpenAI function calling. Tons of models have different ways to do this. We're just using OpenAI here because it's really easy to get up and going. But we're saying return an object with a key matching ID. That is the ID of the matching person if there is one. If there isn't, then return null for it. So this allows our system to easily parse the response, because right now, like if you go to ChatGPT, for example, the output you get is just text, right? And you can't really parse that. So you want structured output. Do I sound like this right now, where I'm just talking about all these things and like I'm hoping you guys can follow along? Well, we're gonna clear that up a little bit. So the overall process, start to finish, you'll get some code and some examples and sample data for all of this, but determine your matching algorithm so you know what data to vectorize, right? Vectorize all existing constituent data based on the primary matching criteria. So if your primary match is address, you would want to vectorize and embed all of your constituents' addresses so that when you searched for an address, you're finding similar addresses in your vector store. You need to load all of those vectors into a vector store, something like Upstash Vector, Cloudflare Vectorize, or Pinecone, among others. There's so many of them out there now. The code samples are going to be using an in-memory vector store just because we didn't need to set up any external services here. Vectorize the primary matching criteria of your input. So this is the person, the donor that you're looking for in your CRM. Query the vector store for similar vectors. Grab the constituent information for that vector so you know that, well, this address was similar. So what constituent is that address for? And then pull all that constituent information. And then feed the matching algorithm, the input data, and the vector data, which are the possible duplicates, i.e. the existing ones already that are in your CRM, into the LLM to get your response. So define the matching criteria. And we're actually going to use AI for this. So it's kind of just like a little bonus. So it's, let's say the steering prompt is, you're an expert at parsing instructions by users that will define one or more primary and secondary matching criteria to use to compare potential duplicate constituents. This is what we're telling the model its job is going to be. And then the user, i.e. someone that works at a charity, might say, well, two constituents are the same if they have the same address. If there are more than one unique constituent at the same address, then use the first and last names as tiebreakers. Well, the AI, ChatGPT here, or GPT 4.0 here, determine that the primary criteria yields address. So let's pull some constituents from Razor's Edge. These are obviously made up. I didn't pull these from anyone's CRM, but we're just gonna have these three people. Sarah and John Connor live at the same address, obviously because Sarah is John's mom, right? And then we have Miles Dyson as well, and he lives at a completely different address. So we're going to vectorize each constituent criteria. So like I said, we're going to have an in-memory vector store. We're going to use TensorFlow embedding. So TensorFlow had a 512 dimensional vector. And then we're going to add the different documents to our vector store so that we can take an address as an input and find similar addresses. We're going to query for similar vectors to the input data. So let's say our input data is Sarah Connor, 309 West Lincoln Ave, APT for Los Angeles, California, USA. Whereas our data in the CRM is using apartment for. So technically not the same address, even though it is the same address, right? So we try and find the two most similar vectors for this address, and we get Sarah and John Connor, as expected. We definitely should not get Miles Dyson here because Miles lives at a completely different address. So finally, the AI that we're going to talk about. How are we actually finding the duplicates here? Well, just walking through it again, we have our steering prompt. We're providing details. We're delineating the sections. We're asking it, does this person match any of these people? These people being the two vectors that we receive from querying the vector store, right? And then passing that in and saying, is there a match here? Based on this matching criteria, can you find a match for my input data? Just breaking down kind of what gets sent internally, because at the end of the day, this is just like instructions being sent, right? There isn't anything like fancy going on here in terms of format and stuff like that. This is just, here's a system prompt. Here's what the user asked for. The data exists. Like, okay, model, do your thing. Remember, this is fancy autocomplete, right? So we're sending in a big chunk of data, and the model is going to analyze that and figure out what the most likely response to that is based on its training information. Ready? Is it going to work? And all this code does work. I'm going to provide you a link to the code so you can reproduce it if you want to. Eureka, it worked. Okay, so there's a lot of stuff here, but let's just break it down. So our input was Sarah Connor, APT4, address with the abbreviation for apartment, right? Our possible duplicates were both Sarah and John Connor, both with apartment 4 written out. Our AI returned the ID for Sarah Connor because it looked at both of those records. It said, okay, well, the addresses are the same. So I'm going to go back and I'm going to look at the last name and the first name. Well, the last name's the same as my input last name, but the first names differ. So I'm going to return Jay the matching ID for Sarah Connor because my input, or the input that Jay provided me, matched first name, last name, and address. Whereas with John Connor, obviously John and Sarah are not the same. So that's it, folks. We did it. We used AI and LLMs to figure out and look up duplicates by leveraging vector stores and prompt engineering. Here's some links if you want to investigate more about all the stuff I talked about. That QR code goes to the slides, all of the text here. There is links behind all that. So yeah, happy to take questions. I don't know if Lizzie's going to join me back on stage right now. I know that there's one question there already. Lizzie, do you want me to just go ahead and start answering?
That sounds great.
Great. Okay. Robert asks, is the LLM here just used as a front interface, or is OpenAI adding something in addition to what could be achieved through machine learning implementation through something like Python's dedupe library? So I'm not familiar with Python's dedupe library, but what's happening here is OpenAI has built and trained models, LLM models, using all of the data that they have scraped. So, you know, you may have seen some lawsuits from like the New York Times, for example, saying like OpenAI scraped our website and used it to train our models without our permission, right? So they have their own model that they would have used machine learning ideas and processes and algorithms on and stuff like that to build out this resulting software that can then take in an input and infer the output. So it's a little bit different than just using, you know, a library. Obviously, I don't know exactly what Python's dedupe library is, but I'm assuming it's not an LLM. LLMs are different than just using a library that would have some kind of internal logic to it. So hopefully that answered the question. If I didn't, Robert, feel free to ask a follow-up question. Leonardo, well, first Jeannie says, before Alexa, there was Clippy. Yes, there was. And Clippy made a couple of appearances here. We all remember Clippy, and if you don't remember Clippy, then we are from a different generation. But Clippy was the first AI, a really bad AI at that, and a really annoying AI at that, but an AI nonetheless. Well, AI, right? It was definitely artificial. I don't know how intelligent Clippy was. Is matching done on some sort of translation table? So that's what our system currently does, is matches and normalizes all of these standards to do the best matching. But with the LLM, no, that's not what's happening internally. Internally, the LLM kind of knows that these words are referenced in the same way. So it can equate the two of them and then has some internal, you know, quote unquote thinking to do to figure out if they're the same or not. But it's different than actually hard coding an algorithm.
All right.
I know we have 10 seconds left. I don't know. Are we going to get
kicked out? I have to bounce to another session that I am also moderating. So I want to thank everyone. I want to thank Jay so much for this amazing presentation. I would encourage everyone to use the people function in Goldcast to reach out to Jay directly if you have questions. If you want to learn more about Trellis or the Social Good Startup Program, feel free to reach out to me directly as well. And thanks, everybody. Take the survey. We'll see you in the next session.
Thanks, everyone, for coming.
Bye.
Bye.